Let's discuss the binomial theorem. The goal of the binomial theorem is to expand binomial expressions without the use of multiplication. For example, x plus 3 is a binomial. If we raise x plus 3 to the second power, we can expand x plus 3 squared to be x squared plus 6x plus 9. Our technique for expanding x plus 3 squared would be to think of x plus 3 squared as x plus 3 times x plus 3, and then use FOIL to expand that expression and simplify to get x squared plus 6x plus 9. Suppose we are asked to expand x plus 3 cubed. We need to think of x plus 3 cubed as the product of x plus 3 three times. We might then group two of the x plus 3's together and expand, and then finally multiply by that last x plus 3. Our answer would be x cubed plus 9x squared plus 27x plus 27. This took multiplication to get from here to here. The binomial theorem allows us to expand these binomials in a somewhat quicker fashion. So even if we had something like x plus 3 to the 19th, we could notice patterns using the binomial theorem and expand this expression without multiplying x plus 3 19 times. Let's look at what happens when we expand an arbitrary binomial, x plus a to the nth power. We'll start with n equals 1 and we'll grow from there. X plus a to the first power simplifies to just x plus a single x and a single a. X plus a squared simplifies to x squared plus 2ax plus a squared. So we start off with the squared variable because our n here is squared, and we end with the constant being squared. Notice the coefficient on the middle term is the same number as the power of the exponent. Now x plus a cubed expands to x cubed plus 3ax squared plus 3a squared x plus a cubed. Again, notice we start off with x cubed, the same power as the exponent, and then we have a coefficient of a 3, which matches our n here, and our variable a here is raised to the first power, our variable x is raised to the second power. And then we have another coefficient of a 3. Now a gets raised to the second power and x is to the first power. And then we end with our variable a, or the constant in that position, being raised to the third power. Now x plus a to the fourth power gives us, again, starting off with x to the fourth, and then our coefficient of a 4, and then we have a to the first, x to the third. Then we have a 6, a to the second, x squared, and then the 4 again, a to the third x, and then finally ending with a to the fourth. So if we stop here for a moment, we do notice that each of these expressions has n plus 1 terms. So here, if n is 1, the expanded expression has 2 terms. Here, n is 2, the expanded expression has 3 terms. Here, n is 3, the expanded expression has 4 terms. Here, n is 4, the expanded expression has 5 terms. We've seen a few times that n value being repeated on the second coefficient, as well as the second to last coefficient. What we're not exactly sure is, where did this middle coefficient, specifically in this example here, come from, this 6? The other pattern I hope that you notice is that the power on each of the terms, or the degree of each of the terms, is always equal to n. So here the degree is 3, so you get a 3. Here the degree of this term, the exponent 1 belongs on the a, and then this exponent of a 2 belongs on the x, and so 1 plus 2 makes 3, and then we have 2 plus 1 makes 3, and then this exponent is of 3. We can notice that pattern in our n equals 4 as well. Here we would have a 1 plus 3, which is 4, 2 plus 2, 4, 3 plus 1, 4. Let's see if we can use these patterns to expand the expression x plus a to the 5th power. So we'll start off with x to the 5th plus, again, that coefficient that matches the power. A will be raised to the first power, and then we'll start descending the powers on x. We don't know the coefficient for the next term, so we'll leave that blank, but we know that a will go up by a power of 1, so it becomes a squared. X will go down 1, so it becomes x cubed. And again, remember, we want those powers here to add up to n, so 2 plus 3 does make 5. My next coefficient is also going to be unknown. A will go up to the third power, x will go down to the second power, and then I get to the second to last term. So I'll again have a coefficient of 5. A will go up to the fourth power, x will go down to the first power, and then finally our very last term will be a to the fifth. So our two middle coefficients here are still unknown. Can we generalize this to the situation where x plus a is to any arbitrary nth power? Our first term will be x to the nth, followed by a coefficient of an n, a raised to the first power, and x raised to 1 less, so n minus 1 power, plus our next unknown coefficient, and then we have a now to the second power, and x loses one more value for its power, n minus 2. This pattern repeats itself until we get to the second to the last term, which will again have a coefficient of n. A will be raised to the n minus 1 power, so 1 less than n, and x will be raised to the first power. And finally, our last term is a raised to the nth power, for a total of n plus 1 terms. What remains to be seen is how we actually get these unknown coefficients that live in the middle of the binomial expansion. In our next video, we'll learn exactly how to calculate these question marks and figure out the coefficients for each term of a binomial expansion. For now, see if you can try to expand x plus a to the sixth power using the techniques we just discussed. Pause the video and then press play to see the answer.